In this lecture, we're going to go over nozzles and diffusers. A nozzle is a flow passage of varying cross-sectional area in which the velocity of a gas or liquid increases in the direction of flow, whereas a diffuser, the velocity decreases in the area of flow. In nozzles and diffusers, the only work that occurs is flow work, and under most conditions, the change in potential energy from the inlet to outlet is negligible. So our energy balance reduces down to 0 is equal to Q plus m dot times H1 minus H2 plus V1 squared minus V2 squared over 2. Typically, the heat transfer with the surroundings is small enough relative to the enthalpy and kinetic energy change to be neglected, which yields 0 is equal to H1 minus H2 plus V1 squared minus V2 squared over 2. So we're going to do an example. We have steam entering a converging diverging nozzle operating at steady state with a pressure of 40 bar and a temperature of 400 degrees Celsius and a velocity of 10 meters per second. The steam flows through the nozzle with a negligible heat transfer and no significant changes in potential energy. At the exit, the pressure is 15 bar and the velocity is 665 meters per second. The mass flow rate is 2 kilograms a second. We want to determine the exit area. Area of our exit is equal to our mass flow rate times the specific volume at the exit divided by the velocity. We don't know the specific volume, and all we know about state 2 is the pressure, so we need another intensive property in order to fix our state. So we're going to do an energy balance. We have 0 is equal to H1 minus H2 plus V1 squared minus V2 squared over 2. I want to solve this for H2 and get H2 is equal to H1 plus V1 squared minus V2 squared over 2. So H2 is equal to 3,213.6 kilojoules per kilogram. This is from table A4 based on my pressure of 40 bar and my temperature of 400 degrees Celsius plus 10 squared minus 665 squared divided by 2 meters squared per second squared. Correct my units. I get that H2 is 2,992.5 kilojoules per kilogram. So now I'm going to look up P is equal to 15 bar and H is equal to 2,992.5. I'm going to get that V2 is equal to 0.1627 meters cubed per kilogram. So my area is my 2 kilograms per second times 0.1627 meters cubed per kilogram divided by 665 meters per second is 4.89 times 10 to the minus 4 meters squared. We're going to do another example. We have air entering a diffuser operating at steady state in 540 degrees Rankine and 15 psi with a velocity of 600 feet per second. The air exits with a velocity of 60 feet per second. The ratio of the exit area to the inlet area is 8. Assuming the ideal gas model for air and ignoring heat transfer, we want to determine the temperature in degrees Rankine and the pressure in psi at the exit. Since this is one inlet and one outlet, we know that m.1 is equal to m.2. And if we employ the ideal gas law, that tells us that A V1 over the specific volume 1 is equal to A2 V2 over the specific volume 2. If I employ the ideal gas law of PV equals RT, we get that A1 V1 P1 over RT1 is equal to A2 V2 P2 over RT2. Our R's are going to cancel. So P2 is equal to P1 times A1 over A2 times V1 over V2 times T2 over T1. That's great. We know almost everything, but we don't know T2. To get T2, we're going to do our energy balance, neglecting heat transfer and potential energy. We're going to get that 0 is equal to H1 minus H2 plus V1 squared plus minus V2 squared over 2. So we get H2 is equal to H1 plus V1 squared minus V2 squared over 2. At 540 degrees Rankine, H1 is equal to 129.06 BTU per pound, and this is from table A22E. So we have H2 is equal to 129.06 BTUs per pound plus 600 squared minus 60 squared over 2, and that's feet squared per second squared. I have to correct my units. At 1 pound force is 32.2 pound mass feet per second squared times 1 BTU is 778 foot-pounds. I get H2 is equal to 136.17 BTU per pound. So now I'm going to look up H2 in table A22E and interpolating yields. T2 is equal to 569.6 degrees Rankine. So P2 is equal to 15 psi times 1 over 8 times 600 over 60 times 569.6 over 540, which is equal to 19.78 psi. In our next lecture, we're going to go over turbines